Hello dear students, welcome you all. In this lecture, I am going to discuss about the change in entropy of a perfect gas, right? Change in entropy of a perfect, or you can say ideal gas, right? Change in entropy of a perfect gas, right? Ultimately, what we will do here in this article, we will derive an expression that will tell us that the change in entropy of a perfect gas depends upon which factors, and under different conditions how this equation behaves, right? So for doing so, let's consider 1 gram of a ideal or a perfect gas. You know very well what is ideal or a perfect gas. Clear? Then let delta Q amount of heat is added to this gas at temperature T, right? So then we know change in entropy from the definition of entropy, it is ds is equal to uh, delta Q upon T, right? This is the relation for change in entropy, that it is equation number 1, right? We know according to the first law of thermodynamics, delta Q is equal to du plus dw, right? So I can put this value here, right? So it will give me ds is equal to du plus dw upon T, right? Now, you know very well that we are considering 1 mole of perfect gas, right? So we know the relation for this gas, Cv is equal du is equal to Cv dt. What is Cv here? Cv here is the specific heat of this gas at constant volume, right? And dt is the rise in temperature. Similarly, if dV is the change in volume of the gas, right? Then this relation du is equal to Cv dt, and also dw is equal to P dV. Clear? But we have to divide it by J. J is here used to divide this equation in order to convert this relation as mechanical equivalent of heat, because dW is the mechanical work. So we are converting this mechanical work into equivalent heat. So then we divide it as a constant J. So this gives us a mechanical equivalent of heat, right? So what I done here, du is equal to Cv dt, right? What we have considered, as we have added delta Q heat into a gas at temperature T, then obviously the change in the temperature of the gas is dt, and the change in the volume of the gas is dV. So then I have these two relations. Now I am going to put these relations here, right? So when you put these values here uh, in equation number this, then you will get ds is equal to Cv dt upon T plus dw is equal to P dV, right, upon J into T. Clear? dw is equal to P dV upon J, or divided by T. So I got this equation in the next step, right? Now you know very well, we know PV is equal to N R T. Clear? So if we take N is equal to 1, then it becomes PV is equal to RT. Clear? So I got PV is equal to RT upon B. Clear? So you can put this value also here. Then in that case, this equation will become, it will become ds is equal to Cv dt upon T, I can write it, plus P now is equal to RT. So RT dV upon J into T. So you get cancelled this. You got only R upon J into dV. We also have B here because P is equal to RT upon B, right? So you got ds is equal to Cv dt upon T plus R upon J, right, dB upon B, right? You got this equation, right? Here R, you know very well, this R is gas constant, J is mechanical equivalent of heat, right? I want to make it clear, I forgot to tell you about it here. We know according to Joule's law, we know heat can be converted into mechanical work and mechanical work can be converted into heat, right? So when we convert mechanical work into heat, the heat produced is directly proportional to mechanical. This is Joule's law. Clear? W directly proportional to mechanical work, directly proportional to the amount of heat. Clear? So we can write W is equal to J into Q. Here J is a constant. Clear? So you can have in that case Q is equal to W upon J. That's why I have taken here Q means this is now a mechanical equivalent of heat, right? dW is equal to, now it is not in the form of mechanical work, now it is heat when we divide it by J. Clear? So this is very clear. This is Joule's law. Now we got this equation, let this is equation number 3. Clear? This is equation number 3. Let it was equation number, I forgot to give this name. This is equation number 2. We started from here. Clear? We put this value according to first law of thermodynamics in this equation. Then we got equation number 2. Then we put the value of du and dw. Then we get equation number 3. Right? Now when we added this delta Q amount of heat in the gas, it goes from state 1, clear, to state 2. In state 1, it has pressure P1, volume V1 and temperature T1. And in state 2, it has pressure P2, volume V2 and temperature T2. Let me consider this entire process as, clear? We have a given 1 gram of gas, we added delta Q amount of heat in that gas, and then we got the change. Clear? Initially this was the property of this gas, and finally this. Now if we want to find out the total change in the entropy of this gas, then we have to do the integration within these limits. I means S will be equal to integration 1 to 2 ds. Clear? State 1 to state 2, that is equal to integration of the right hand side, Cv is constant, so dt upon T from state 1 to state 2 plus R upon J, again it is constant, so I took it outside, 1 to 2 dV upon B. So this is the integration of this equation number 3. So when you will simplify it, what you will get? You will get S2 minus S1, clear? That is equal to Cv log of T2 minus T1, so I can write it as T2 upon T1. So when you will take the integration, you will get log of T, and you put the limits log of T2 minus log of T1, so we can write it in this form here. That is equal to, that is equal to, but it was plus here, plus R upon J, right, into log of natural log of B2 upon B1 again here. How it is? Because you will get the integration of this as log V, you put the limits log B2 minus log V1, so it will give you this equation, right? Now you know very well Cp minus Cv from the thermodynamics, it is R upon J, clear? So when you put this value here, this in this equation here, and also you have one relation, that is P1 B1 upon T1 is equal to P2 B2 upon sorry T2 from the thermodynamics. So it will give me T2 upon T1 is equal to P2 B2 upon P1 B1. If I rearrange this, I took T2 here, T2 upon T1, I took this toward this side. So now I am going to put these two values, this here and this value here, clear, in this equation. So then I will get S2 minus S1 is equal to CV log of T2 minus T1, T2 upon T1 means P2 B2 upon P1 B1, clear, plus R upon J means Cp minus Cv into log of B2 upon B1, clear. So when you will expand this, you will get Cv log of this is P2 upon P1, clear, bracket, plus Cv log of B2 upon B1. How? Because they are multiplications. In multiplications, P2 V2, P1 B1. So I separate them. So in term of log, it will become plus here. Plus this term Cp log of B2 upon B1 minus Cp, it is Cv log of B2 upon B1, clear. So Cv log of B2 upon B1 get cancelled. So you got Cv log of P2 upon P1 plus Cp log of B2 upon B1. So this is let equation number 4. Now this equation is the desired equation that tell us about the total change in entropy of a perfect gas or a ideal gas, clear, during this entire process, clear, that we were looking at from the beginning. So we arrived at this equation, clear. Now we can have different situations, right? Suppose the process takes place at a constant pressure, means P1 is equal to P2, clear. Then in that case, what will be the situation? I can put here S2 minus S1. P2 upon P1 will give you 1, log 1 means 0. So you will get it is equal to Cp log of B2 upon B1, clear. So this is the required relation. You can even further convert it. B2 upon B1 is equal to T2 upon T1. How? From here, this, if P1 is equal to P2, you will cancel out. So you will get, I can write it in this way, P1 B1 upon T1 is equal to, it was this equation, clear. So if P1 is equal to P2, they will get cancelled out. B1 upon T1 is equal to B2 upon T2. So you can write B2 upon B1 is equal to T2 upon T1 here. So you can put, it is give you log of T2 upon T1. So this is now equation change in entropy in terms of change in temperature. This is the first situation. You can now by using this equation you can solve any numerical problem. Similarly, you can have also another situation where this process takes place at constant volume, means B1 is equal to B2, clear. This can be the situation. If you put it here, this term will become 0 because B2 upon B1 1, log 1 0. So what you will get? Cv log of P2 upon P1, clear. This is S2 minus S1. Again, I am going to use this equation. Now volume is constant. It means this is going to be cancelled. So P2 upon P1 is equal to T2 upon T1. Then in that case, you can see from here, when B1 got cancelled, you took T2 here, so it becomes T2 upon T1 is equal to P2 upon P1. You took it toward this side. So you will get the situation changed, and you will get Cv log of natural log of T2 upon T1. So this is another form of this equation when volume of the system remains constant. Clear? Similarly, if the change is isothermal, right? Isothermal means when there is no change in the temperature. Now look at this equation. In this equation, you will get you will go to the equation number, then this one. I have actually put all the values. So in that case, it was the equation. Yes, this one. Clear? So then we have modified this equation. So now I am going to apply the condition when the process takes place at constant temperature, then this factor will become 0. So we will get S2 minus S1 is equal to R upon J log of B2 upon B1, right? S2 minus S1 is equal to R upon J log of B2 upon B1. Clear? So this is the required relation when the process was isothermal. So now we have three different conditions. This is for isothermal. This is for isochoric when the volume is constant. This is for isobaric when the pressure is constant. Then we have this equation. Clear? So this is all about the change in entropy of the perfect gas. Clear? We derived the equation for it. That equation was this equation number 4, right? Then basically it was this equation, right, that we derived, but we modified this equation by replacing T2 upon T1 with this and R upon J with this. So then when we modified this equation, we got this one. So when we applied different conditions on this equation number 4, right? So this is all about the change in entropy of a perfect gas. This article is very, very important in terms of numerical problems, right? You can be given a numerical problem where you will be given all the factors and you will be asked to find the change in entropy of this ideal gas or perfect gas, right? So you can use any of these different equations, either this one or this one or this one, depending upon the situation, right? So thank you very much.